So yesterday, we have described two techniques to reduce the interference that enter in the beam pattern through the side lobes. And basically as the effect to bias the measurement of the power coming from the steered direction. So we want to measure the power coming from a specific direction. We steer the beam in that direction, but through the side lobes, the power generated by other sources coming from different angles may enter in the beamformer, and it is attenuated by the side lobes, but obviously not completely eliminated. And the effect is that it biases the measurement. So a way to reduce this bias is to reduce the side lobes. And we have seen two techniques to reduce the side lobe. The first one, which is called shading or windowing sometimes, or shaping. Basically, it's a non-adaptive technique that relies on the use of windows. And this kind of technique should be applied when we don't have a priori information about the directional arrival of interference, of disturbance. So if you don't know where the disturbance will come from, we try a priori by design to reduce the side lobes. And to reduce the side lobes, we should apply a window. And we have seen that there are many different kind of window because each of them can guarantee a different trade-off between the masking problem, so reduction of the masking problem that is obtained by reducing the side lobe. But on the other side, the other unwanted effect is that we worsen the resolution, because if you lower the side lobes, you widen the main lobe, and so you worsen the resolution. The second technique, which is called null steering, can be applied to those cases where we know perfectly the directional arrival of the interference. So we know exactly where another transmitter is, so which is the directional arrival for this other transmitter, and we want to put a null in the beam pattern in that direction. And we have seen how to put the null, so how to solve the optimization problem with constraint by using the Lagrange multiplier method. Actually, we can solve the problem in a different way, and I will show briefly this different approach to come up with the same solution. Why? Because with this different approach is easier to generalize the result and solve the problem when we want to put multiple nulls in the beam pattern. So if you remember, we reconsider the optimization problem with constraint that was solved to find the classical beamformer. So with the non-distortion, with the distortionless constraints, which is A Hermitian theta, theta is the steered direction, H equal to 1. So this is the distortionless constraint. So we want that the signal that comes from the steered direction passes undistorted through the beamformer. And we added the null constraint. So A Hermitian theta j, H equal to 0. So we want to cancel the signal that is coming from directional arrival theta j, because it is considered to be an interference. Okay, so if you take this matrix that has 2 rows and m columns, and you call this matrix A, and you call this two-dimensional vector B, you can express the two constraints as linear constraints with matrix notation. So in other words, the problem that we want to solve is a linear system of equations where we have two equations. So the number of equations is equal to the number of constraints with n unknowns. And the unknowns are the element of the spatial filter H of the beamformer. Now, because m is clearly, so the number of sensors much greater than 2, this is an underdetermined linear system. So it has infinite solution. But if you remember, we were looking the solution, so the vector H that satisfies this equation having the minimum norm. So there are infinite solutions to this underdetermined linear system, but we want not only one of the infinite solutions, we want the one with the minimum norm, because we want to minimize H Hermitian H, which is the energy of H, so which is the Euclidean norm square of H. Now, I don't know if you are familiar with the solution of underdetermined linear system. So the minimum norm solution, but it can be proved that the minimum norm solution to this underdetermined linear system is given by the so-called Moore-Penrose pseudo-inverse, which is a sort of inverse for a square matrix, because the matrix is square. It's a fat matrix with 2 rows and m columns. So, I mean, if m is equal to 2, A is square, and the solution to this system is the inverse of A times B. Now, because m is greater than 2, A is rectangular, so we can't calculate the inverse. Well, it can be proved that the solution, the minimum norm solution, is provided by the pseudo-inverse, which is a generalization of the concept of inverse to square matrices. And the pseudo-inverse is defined as A Hermitian that multiplies the inverse of A Hermitian times B. I mean, this is correct provided that A is a full rank matrix. So the matrix should be in this case 2. If you calculate this quantity, the pseudo-inverse, so I will skip the details. Obviously, you come up exactly with the same solution that we derived yesterday by solving the optimization problem by using the Lagrange multipliers. So clearly the solution is exactly the same, the one that we derived yesterday, but it's an alternative approach to find that solution. So it's very easy to generalize, because if you want to put multiple constraints, so for example, if you want to put not only one, but L nulls in the beam pattern, because there are L interferences with known directional arrival. So if we want to put nulls in the beam pattern for the directional arrival θ1, θ2, θL, so the constraints are expressed by these L plus 1 equations. So we have one distortionless constraint plus L nulls. So in total, we have L+1 constraints, and we can express the constraints as a usual matrix equation, AH equal to B. The only difference is that A and B now are an extension of the previous A and B. So A has dimension L+1 by M, and B has dimension L+1 by 1. So L+1 is the number of constraints. So again, we want to find the minimum Null solution of this underdetermined linear system of equations. This is underdetermined if L+1 is smaller than M, obviously. So L should be strictly lower than M-1. If you have equality, at that point you have a number of equations that is equal to the number of unknowns, A squared, and if it is full rank, can be inverted. But the system is underdetermined if L is strictly lower than M-1. In that case, the minimum Null solution again is provided by the pseudo-inverse. So you calculate the pseudo-inverse and you find the solution. In MATLAB, if you are familiar with MATLAB, actually there is a command least square minimum norm. So this command here that allows to solve this problem. So you pass the matrix A, you pass the vector B, and you get the solution H. And then there is the flag that tells you if in the calculation of the pseudo-inverse there are problems, because if A is not full rank, you cannot calculate this inverse and you have a problem. These are three numeric examples. So for example, we have a Euler array with 16 elements. We want to steer the beam at 0 degrees, and we want to put 6 nulls at these 6 angles, -70s, -50, -20, 20, 50, 70. So you find the solution, and then you plot the beam pattern, and as you can see, you have that the main beam more or less is the same as the classical Euler beamformer, but you have the nulls for this angle, -70, -50, -20, 20, and so on. So this is the way you can put nulls in known direction. If you want to steer the beam at another angle, again, you change the first constraint, you steer the beam at 30 degrees. The other 6 constraints are the same. You solve the problem, you plot the beam pattern, and this is what you get. So you have the main beam at the desired direction 30 degrees, and you have the 6 nulls at the desired direction arrival. Only one issue. It can be shown that if you want to put the nulls too close to the steered direction, you may have problems. And for example, in this case where the steered direction is 30 degrees, but you want to put nulls close to that. So for example, at 24 degrees and 38 degrees, what may happen is that because you are trying to put the nulls very close to the main beam, it may happen that maybe the main lobe is made smaller, but the result is that you obtain side lobes, higher side lobes. So you worsen the problem of masking because you are trying, you want to oblige the beam pattern to have nulls very close to the steered direction. And the counter effect of this could be that you observe an increase of the side lobes. Clearly, it is something unwanted. So we should be careful. Okay, this is all for this part. So now we should start talking about adaptive beamforming. Okay, so why adaptive beamforming? Adaptive beamforming basically has the purpose to reduce the effect of interference better than what can be obtained by using classical beamforming. Now, we have seen the shading and the null steering techniques, but the shading is non-adaptive. You decide a priori without knowing where are the interferences. You decide a priori how you want to modify the beam pattern. You select a window with the goal to reduce the side lobes, and that's it. And then you can't change it. On the contrary, the null steering techniques allows you to put the nulls exactly in the direction of the interferences, but if this direction arrival are unknown, you cannot apply this technique. Now, the problem of the classical beamformer is that the beam pattern is determined by the geometry of the array. Remember, is a meshed filter to the array response. So it does not attenuate more where it is more necessary, more useful. So the classical beamformer is not adaptive in the sense that it always does the same. Wherever is the directional arrival of the interference. Now, the idea of adaptive beamforming is attenuate more where it is more useful, and where it is more useful, where you have more power from interference. So attenuate more where it is more necessary. But the problem is that we don't know a priori where it is more necessary, because we don't know a priori where the interference comes from. If we knew, we could use the null steering technique. But in most of the cases, we don't have this a priori information. So the idea is to use in some way the received data to acquire this information and to update the weight coefficients, so the impulse response of the spatial filter, based on the received data. So the H, the impulse response of the beamformer, is made dependent on the received data. So the beamformer becomes adaptive. Now, as you will see, this possibility guarantees that the interference can be suppressed in a better manner. So we use in a better manner the m degrees of freedom, so the choice of the m unknowns that are the elements of the vector H, because we try to attenuate more where it is more useful. Now, the problem is how to achieve this goal, obviously. Now, remember what is the objective of implementing a beamformer, a special filter. In general, what we observe is made by a signal of interest, but in the data you can have also obviously thermal noise, which is always present. You can have clutter, you can have jammer. So the scope of the beamformer is to separate as much as possible the signal of interest from the disturbance based on the different directional arrival. So the selectivity guaranteed by a spatial method is in the angle domain. Remember, temporal processing allows to separate signal from disturbance based on their spectral content, so based on how the power is distributed in frequency. Spatial processing, it allows discrimination between signal of interest and disturbance based on the directional arrival. So in other words, the idea is to make the weights, so the elements of the impulse response of the beamformer, to depend on the input data, and to depend on the input data in some manner that we have to understand this morning. So what is a good adaptive algorithm that allows to achieve this goal by making the filter adaptive? So by making its impulse response dependent on the observed data. To find this adaptive algorithm, so to find the optimal weight vectors, so the optimal H, we have to choose some optimization criteria. So how do we measure the optimality of our algorithm? There are different methods. Some methods require the definition of a reference signal. Some methods are blind. We will see two of them, the most important two, okay? So let's start assuming that there is only one source or one target. And then we collect n snapshot at the output of the array made by m sensors. So the structure of one snapshot y of n is the one that you know very well. It's the array response calculated at the direction arrival of the source or of the target, multiplied by the complex envelope of the signal generated by the source or reflected back by the target, plus disturbance. Disturbance can be composed by noise. The noise can be white if it is thermal noise, or can be correlated, for example, if it is clutter. And then you have a directional interference that typically is man-made, so generated with the purpose to disturb the radar. Now, the beamformer output of a general beamformer, as you understood, is because the beamformer is an FIR, discrete time linear time invariant filter. So we can express the output to this partial linear filter as H Hermitian Y of n. So the filter is linear. So we have at the output the contribution of the signal of interest plus the contribution of the disturbance. Now, as I said, the goal of implementing this special filter is to allow the signal of interest to pass undistorted and to reduce, to attenuate as much as possible the disturbance. And because we are talking about special filter, I repeat, the discrimination between the signal of interest and the disturbance is made based on the directional arrival. So what are the two most popular criteria that have been used in adaptive beamforming? I mean, they are very reasonable. And, I'm sure you have find similar criteria in many other applications related to detection and estimation of signals. The first one, the first criterion is to minimize the mean square error. So the filter H, the beamformer, should be designed in such a way to minimize the mean square error. The mean square error is what? Is the power of the difference between the output of the beamformer, which is H Hermitian Y, and some desired signal. D represents the signal of interest that we want to isolate from the disturbance. So for the time being, let's say that D is the desired beamformer output. Then we will see. So a reasonable approach is find H that minimize the power of the error between the desired beamformer output and the true beamformer output, which is given by this term. The second criterion is also very reasonable because it says that we should maximize the signal to disturbance ratio. Now, in this example, the disturbance is interference plus noise. So we want to maximize the SINR output. So at the output of the beamformer. So we want to find the beamformer that maximize the signal to disturbance ratio at its output. And what is the definition of this signal to disturbance ratio? It is the power, the statistical power of the output of the beamformer due to the signal to the statistical power of the output of the beamformer due to the noise, due to the disturbance. So this is the ratio of the two statistical powers of signal and disturbance at the output of the beamformer. This is what we should try to maximize. So they are two different criteria, and we will try to understand which is the relationship with them. So let's start. Let's start with the first one. We want to minimize the mean square error. Now, if you are familiar with the bias estimation, I think you have already encountered the concept of Wiener filter. And the Wiener filter is nothing but the linear minimum mean square error estimator for some specific problem where we want to reconstruct a random signal in the presence of random disturbance. So the solution of this problem is exactly the Wiener filter. So what you have probably already seen studying bias estimation. But anyway, we will derive. So the objective is to minimize the mean square error between the desired signal at the output of the beamformer and the actual beamformer output. So, okay, as I already said, the solution of this problem is because we minimize the mean square error and the solution is linear, is forced to be linear. What we are looking for is actually the linear minimum mean square error estimator, which is the Wiener filter. And this is the solution, but how do we find this solution? So we take the mean square error, we start from the definition. The first step is to express the modulo square as the product between this scalar and its conjugate. But because it's a scalar, we can put the Hermitian here. The Hermitian is the transpose conjugate. So we calculate the Hermitian. So we have the Hermitian minus y Hermitian h. Then we calculate all the products. So we get 4 terms. And then we calculate the expectation. So the first term is the power of D, the power of the desired signal. The second term, remember, H is deterministic. So when you calculate the expectation, you have the expectation of this vector. This vector contains all the cross correlations between what we observe at a given sensor and the desired signal. So it is the cross correlation vector between Y and D, between what we observe and what we want to estimate. Third term is just the Hermitian of the second. And then we have a last term. Again, H is deterministic. When you calculate the expectation, you get the expectation of Y Hermitian. And this is just the spatial correlation matrix of the observed data. So the mean square error has a quadratic dependency on the unknown vector H. So we calculate the gradient and we set the gradient equal to 0. This is the classical approach to find the solution. In this case, because the dependency is quadratic, when you calculate the gradient, you come up with a set of linear equations. So it's very easy to solve. So this is the gradient. You set this equal to 0. And so the solution is the inverse of Ry that multiplies the vector Ryd of the cross correlation. Ry is Hermitian. So when you calculate the Hermitian is irrelevant, so you can remove. And so this is the solution. And this is nothing but the Wiener filter, the classical Wiener filter. So it's the linear minimum mean square error estimator. Now, what is Ry? We already understood. We know well. It's the covariance matrix of the signal plus interference plus noise. What about this cross correlation vector? So remember, it's the cross correlation between what we observe, so the M samples at the output of the M antenna, and the desired signal. So this is a vector. This is an M-dimensional vector. Now, if Y has this structure, so if there is only one point-like target or point-like source, what is the expression of Ry and Ryd? Okay, the covariance matrix we know is the power of the source that multiplies this rank 1 matrix plus the spatial correction matrix of the wall disturbance. But in this case, what is the desired signal? So which is the signal that we would like to isolate, to separate from disturbance at the output of the beamformer? It is the signal generated by the source. So in our application, D of n is nothing but S of n. And so this vector here, Ryd, is the expectation of Y, that is this one, that multiplies S Hermitian of n. Now S is a scalar, you can write S conjugate. So you calculate the product. The expectation of the first term is the array response that multiplies the power of the source. The cross correlation between W and S is 0 because signal and disturbance are typically uncorrelated. And so if you replace this in the general expression, we find that this is the solution. So the optimal minimum mean square error estimator is no more a filter matched to the array response because of the presence of this matrix here. So it's the inverse of the data correlation matrix that multiplies the array response. So it's no more the matched filter because of the presence of this matrix here. Now, actually, you will see that any spatial filter whose impulse response is proportional to this remains optimum because the filter is linear. So, I mean, it does not affect the signal-to-noise ratio, so it does not affect the performance. So you don't need to know the signal power. You can use any constant K, and the filter remains the optimal one. Okay, what about the other criterion? So what about if we decide to adopt the second criterion? So the maximization of the signal to interference plus noise ratio. Again, the solution is again the Wiener filter. Sometimes this is called Wiener-Roth solution. The Wiener-Roth equation are the equation that when you study bias estimation, you find when you apply the orthogonality principle. So the Wiener filter is the solution of the Wiener-Roth equation. So there is a very strong relationship between the two solutions, but let's derive the second one. Okay, So we have signal plus noise. Okay, so let me go back. So this is the signal vector plus disturbance. So by definition, the correlation matrix of the signal vector is the expectation of S as Hermitian, and so it can be expressed as the power of the source, the power of the signal, that multiplies the normalized correlation matrix. So this is the matrix that has 1 on the main diagonal, and then all the off-diagonal elements are the correlation coefficient between different sensors. Then we have the covariance matrix, correlation matrix of the disturbance. So if it is jammer plus noise, it is the sum of the covariance matrix of the jammer plus the covariance matrix of the noise. And if you remember, we already described these steps. So if you put in evidence the total power that we call sigma W square, so the power of the jammer plus the power of the noise, we can express the disturbance normalized covariance matrix in this way. So we have this ratio times Qj plus this ratio times Qn, and we can express this and this in terms of the jammer to noise ratio. The jammer to noise ratio is the ratio between the power of the jammer to the power of the noise. And so we can express Rw as the total power of the disturbance that multiplies Q, which is the normalized correlation matrix of the total disturbance. Okay. Now we have the output of the beamformer. We have the signal contribution plus the disturbance contribution. So the signal to noise ratio at the output is the ratio of the two statistical powers. Now, we can express the modulo square as the terms inside the modulo that multiplies its Hermitian. And we do the same at the numerator and at the denominator. So we calculate the Hermitian. We bring outside H because it is deterministic. So on the left and on the right, at the numerator and at the denominator. So we get this. Okay, now what remains in the expectation, at the numerator, by definition, this is the covariance matrix of the signal, which is sigma S square QS. At the denominator, we have the total power of the disturbance, sigma W square Q. Now, why we express RS and RW in this way? Because now, having put in evidence the power of the signal and the power of the noise, we can say that this is the signal to interference plus noise ratio at the input of the beamformer. Because this is the power of the signal at the input of the beamformer, this is the total power of the disturbance at the input of the beamformer. So the signal to noise ratio at the output is the signal to noise ratio at the input that multiplies this quantity here that depends on H. Now, this quantity is typically called array gain because it represents the factor by which the signal to noise ratio increases at the output of the beamformer. So you implement a special filter with impulse response H, and the signal noise ratio changes from the input, and the amount of change, we hope the amount of increase, is called array gain. So the array gain is a parameter that tells you how much the signal noise ratio improve thanks to spatial filtering, thanks to the beamformer. So by definition, it is the ratio between the signal to interference plus noise ratio, or signal to disturbance in general ratio, at the output divided by the same quantity at the input. So it's a very important parameter that tells you how well you have designed your beamformer. And it depends on how you design the beamformer, so it depends on the choice of age, but it also depends on the correlation, spatial correlation structure of the signal and of the total disturbance, because you have all these ingredients here. So the second approach aims at choosing H, so designing the beamformer in order to maximize the output signal noise ratio. Now, because the signal noise ratio at the input does not depend on H, so to maximize SINR output is equivalent to maximize the array gain, because this constant, so the SINR at the input, does not depend on H. So I repeat, to maximize the signal to interference plus noise ratio is equivalent to maximize the array gain. So it's the same.